So in this video we are going to apply the ratio test for the convergence of an infinite series to power series to try and work out their radii of convergence. So you need to be well up on the ratio test in order to follow what we're going to do in this video. So if you aren't well up on the ratio test, I have a video that precedes this one in the playlist on calculus where we look at the ratio test and understand why the ratio test is true in detail. So I want you to understand that before coming on to this video, because I'm not going to re-explain why the ratio test is true here. So power series then. Power series, in my opinion, are one of the most fascinating parts of calculus. In fact, I would say, for me, they're the most fascinating part of calculus. Differentiation, integration, differential equations, they're incredible, incredibly powerful. You know, when you see the problems in physics that differential equations are able to solve, which if you were trying to do that or trying to think how to do that and you knew nothing about calculus, you'd think, good gracious, this is impossible. Take, for example, the problem of like a charged particle moving through an electric field that isn't just a constant electric field, it changes depending on your position. Then the moment, you know, for a certain starting position of the particle, you can work out what the force it's going to experience is. So if you know what its starting position and starting velocity is, you can then work out from the force using Newton's second law what its acceleration will be, and then you can work out how its velocity is going to change, and you can work out how it's going to move for a split second from its initial velocity. But then the moment you have moved that tiny bit, the electric field might have changed that tiny bit from that movement. So, you know, the electric field we're assuming isn't just a constant electric field. So once it's moved, the electric field it's now in is different. So the force it's going to experience is totally different. So how on earth do you get control of that infinitesimally changing scenario? It's incredible, and calculus manages to do that. You would think it's impossible and you would just have to build better and better numerical solutions, which is what we do when actually the differential equations aren't tractable. But the fact that for some problems you can actually solve them and get these perfect solutions, it is incredible. So calculus is incredible, but compare that to infinite series. I remember when I was 17 and was first exposed or first taught Maclaurin and Taylor series. It's absolutely incredible, breathtaking, it utterly unbelievable that these infinite series involving these derivatives somehow converge to the initial function that you took derivatives of. It's absolutely unbelievable. And you know, I remember my teacher actually getting up this demonstration where it was showing better and better or higher and higher power versions of the Taylor polynomial, and it showed it getting closer and closer to the actual function you want. I think the most beautiful examples are probably sine and cos, or the most classic examples certainly, where you watch the higher and higher power Taylor polynomials getting closer and closer to sine and cos, you know, making more and more of the sinusoidal waves as they get higher and higher powers. It is incredible. And you know, when you see that, you want to know, why on earth does it work? Why does that work? So power series are very intriguing, and we're not, I'm afraid, going to answer the question of why does the Taylor series work. That's a topic for another video, Taylor's theorem. In this video, we're just going to look at how we can decide for a power series for which values of x it's going to converge at all, and then how we can decide for some values of x it's going to actually not converge and it's actually going to diverge. And this is the concept of the radius of convergence, the bunch of points in the real line where this power series actually converges to a finite value and when it doesn't. And of course, for the famous examples that we see the Maclaurin and Taylor series for, like e of x and sine of x and cos of x, their radius of convergence is the entire real line everywhere it converges. But for other power series, more generally, that you can imagine, the radius of convergence is smaller. There's only a subset of the real line where it's actually going to converge to a finite value, and then for other ones, the actual series isn't going to converge at all. It's going to be divergent. So after that spiel about how much I love power series, the one true love in my life, let's now actually get to business. So we're going to apply the ratio test to power series. Let's start with a power series. So the sum from I is equal to 0 to infinity. I almost said 1 to infinity there. We don't want from 1 to infinity. Here we do want the 0 because we do want the x to the power of 0 term of, and then we'll call the coefficients of the powers of x, we'll call them ci, and then, now we could put x to the power of I, but actually more generally we might want to center the power series around anywhere on the real line, so we'll put x minus a to the power of I, where a is some element of the real line, and just drawing a picture, if this is 0, this might be a, and this is the point around which we're centering the power series and around which the radius of convergence will be. And we'll find actually that these collection of points where the power series is convergent usually actually form like a nice little interval of equal radius on both sides, which is why we often call it the radius of convergence. So we're going to apply the ratio test then to this power series to try and decide when it converges or not. And the ratio test is a brilliant one that often works for power series. It's not going to work for all examples of power series, but certainly for many of the examples, many of the classic examples that you see for Maclaurin and Taylor series, it will work, and you will be able to prove at the very least that these power series that you've constructed do converge to something. We're not going to prove that they actually converge to what we want them to converge to, but we will prove that they converge to something with this. So the ratio test then, so the thing we do is we look at the limit as n approaches infinity of the absolute value of the ratio between neighbouring terms. So we'll have cn plus 1, so the n plus 1th term, x minus a to the power of n plus 1 over cn x minus a to the power of n, and that absolute value. And then what the radius test tells us, what the ratio test tells us is that 1, if this limit exists, and we need the limit to exist if we're going to use this test, but if it exists and it is greater than 1, you can immediately conclude that the series is divergent, not convergent at all. If it's equal to 1, then you can't conclude anything, inconclusive. And if it's less than 1, that limit, then you can conclude that your series converges. That's what the ratio test tells us. Now, a bit of cancellation here then. So that x minus a to the power of n is crying out to be cancelled away. So we've got mod of cn plus 1 over cn, can't do anything about that, times mod of x minus a to the power of 1. And I've just split the modulus up and I can do that. Nothing dodgy going on there. So I've just cancelled the x minus a to the power of n and then just pulled that x minus a out. So we've got mod of x minus a. Now, as far as this limit is concerned, that x isn't changing. These are changing with n. This is a sequence in n, but this is a constant as far as that sequence in n is concerned. So basically you've just got the limit of a constant times this thing, which is the actual terms of the sequence. And basic fact of limits, you can then pull that out. So this is equal to mod of x minus a times the limit as n approaches infinity of the absolute value cn plus 1 over cn. And don't get scared by the absolute value sign. All that's saying is that rather than worrying about what the signs of these things are, all we're actually interested in is how big they are. Really, this is just, you could split this up into the absolute value of cn plus 1 divided by the absolute value of cn. So really we're just looking at the ratio of how big subsequent terms are to one another. So don't get scared by the absolute value sign. It's very, very simple. It's actually making things simpler. It's getting rid of the flitting between positive and negative that might be there. So this overall thing then, for our power series to converge at that value x, this needs to be less than 1 for us to conclude that it converges using the ratio test. And if it's greater than 1, you can immediately conclude it's divergent. At the value it's equal to 1, you've got a problem. You can't conclude anything. It might be convergent, it might be divergent. So This thing then, we can give this a simpler name, we'll just rename it rho, and all it is it says look at these coefficients of the power series and look at the ratio of subsequent ones, so Cn plus 1 divided by Cn. You're only interested in the absolute value of that ratio, so make these both positive and look at the ratio between how big they are and find what that limit is. And if this limit exists, then that limit is going to exist. Unless, of course, x is equal to a, in which case that vanishes it away and possibly this could be going to infinity, but we'll discuss that more later. But in most cases, this is going to exist if this thing exists, and it's going to be some finite value, so we'll call that rho. And now we've got a nice equation here that mod of x minus a times rho must be less than 1, and if that is satisfied, then the series is going to converge. So just to give an example, let's say rho was equal to 2. What that then tells us is that x minus a must be less than a half, because I've just divided through by the 2. And what that is telling us in terms of a picture, or in terms of this picture that we've got already up here, is that it's going to converge for all those x values that are a distance away from a of less than a half. So you could draw on this little interval here. This is a plus a half, this is a minus a half, and on that little interval, all of those points inside there, this is going to be satisfied here, and indeed this limit overall is going to be then less than 1, and you can conclude that the power series is going to converge. At those two boundaries, so a plus a half and a minus a half, then the distance is actually equal to a half, and in that case you've got half times 2 is the overall answer to this, which is 1. And you're then in this realm here where you can't actually conclude. So in those two boundaries there, you can't actually conclude whether the series is going to be convergent or divergent. Beyond there, this distance is now going to be greater than a half. So you're multiplying it by 2 here, and that thing that you're going to overall end up with then is actually going to be greater than 1. And you can then conclude that it's divergent. So beyond here, it's divergent. So that's what I was saying earlier. You've got this beautiful little symmetric interval around the centre of the power series A where it's converging, and that's why we call it the radius of convergence of the power series. In complex calculus or complex analysis, the equivalent thing becomes like a little disk in the complex plane, a little circle, so it's even better there, the name radius of convergence, but in the real line it's just going to be the one-dimensional version of that, which is an interval. So more generally, if we go back to the general rho rather than rho is equal to 2, then the radius of convergence will be size 1 over rho. So we'll have that mod x minus a must be less than 1 over rho, and if that's satisfied, you can conclude that it's convergent. So again, drawing a little picture here. So here's our a on the real line. You can go forward to the a plus 1 over rho, and you can go backwards to a minus 1 over rho. And on all of these points inside that interval, this inequality is going to be satisfied, and therefore overall this thing is going to be less than 1, so you can conclude your power series converges. At these 2 points, in that case you'll have that overall this equals 1, and therefore you can't make a conclusion. And then beyond those points, you'll have that this is greater than 1, and therefore you can conclude that the power series is divergent. So you've just got 2 points where you don't know what the answer is, and it might be the case that you can plug in those specific values of x in and see what the series you end up with is, and you might be able to analyse in some other way whether it's convergent there or not. And it might be the case that both of them aren't convergent. It might be the case that one's convergent, one's divergent, etc. So you have to look at those individually. You can't make any conclusions from this test. So let's look at some examples to illustrate this. So we'll take a very famous example as our first example. So sum from I is equal to 0 to infinity of x to the power of I over I factorial, very famous power series. So let's write down the first few terms of this. So it's 1 plus x squared over 2 factorial, which is 2, plus x cubed over 3 factorial, plus x to the power of 4 over 4 factorial. And I'm sure all of you know that that amazingly converges to e of x everywhere along the real line. Now, we're not going to prove that it converges to e of x everywhere in this video. What we're going to prove is that it does converge to something everywhere on the real line, which is at least a step forward. Not quite where we'd like to be, but at least it's something. So we're going to do this by applying the ratio test, as we've done for the entire topic of this video. So we're going to look at this limit then, the limit of the ratio between the terms. Now, of course, the ratio between the coefficients of the terms. So, of course, the coefficients are all positive in this case, so we don't need to worry about the absolute value signs. So it's just going to be the limit as n approaches infinity, and then the coefficients are just 1 over n factorial. So at n plus 1, it's 1 over n plus 1 factorial, and then we're dividing it by 1 over n factorial, which is just the same as multiplying it by n factorial. So overall this becomes this. That cancels to limit as n approaches infinity of 1 over n plus 1. Now as n goes to infinity, this goes to 0, vanishes away, so this is equal to 0. And now we didn't actually budget for that in this formula here, did we? Because we always assumed that the multiplicative inverse for rho would exist. Oh, and by the way, something I potentially didn't justify enough here, rho is always going to be a non-negative value, because remember, it's the limit of this sequence, and this sequence is all non-negative values because of the absolute value sign there. So you're never going to have to worry about rho somehow ending up being a negative number. So we could divide through there or multiply by the multiplicative inverse without having to worry about flipping the sign of the inequality, because we knew rho was going to be non-negative. So the only scenario that we didn't budget for was what if rho is actually equal to 0, in which case the multiplicative inverse doesn't exist. But in that case, this is nonsense. You have to go back to this formula here, which is still valid. So in that case, rho is 0, so you've got 0 times this, and you can see that that's true. This inequality is then true for whatever x you like. Now, our power series is centered around a is equal to 0, so our equation becomes mod of x times rho needs to be less than 1, and now rho is equal to 0, so you can see for all x is an element of the real line, that is true. So the criterion for convergence is met at every single x value in this case. So you can conclude that this power series is going to converge everywhere on the real line, and we've concluded that using the ratio test. So I at least find that quite impressive, that this quite simple test, the ratio test, has proven that this incredible power series converges for absolutely every x as an element of the real line. It hasn't proven what it converges to, but it has proven that it converges to something finite. And that's a step forward. So let's do another example. So the next example we're going to take is sum from I is equal to 0 to infinity of xi. So this is 1 plus x squared plus x cubed. So really it's the geometric series where we now have a variable x which we can vary over all values of the real line. So of course you probably know already where this converges and where it doesn't, but we'll apply the test regardless. So using our test then, so we want this limit of the ratio of the coefficients. So the coefficients are all 1 in this case, so their ratio is therefore also 1, so the limit of that is basically just the limit of a sequence of 1s, so it's just 1, 1, 1, 1, and that limit is equal to 1. So now the equation for convergence is going to be mod x times 1 needs to be less than 1, because that's what this rho is equal to. And again, the power series is centered at 0, so that we don't have the x there. So we get, therefore, that mod of x needs to be less than 1. When mod of x is equal to 1, by the ratio test, that corresponds to this case here. This overall limit is equal to 1 in that case, so it's inconclusive. When it's greater than 1, that will make the overall limit greater than 1, and therefore you can conclude that it diverges. So in terms of the radius of convergence of this, we know that for mod less than 1, so for this interval -1 to 1, everything's fine and it converges, which is a familiar result about geometric series. For greater than 1, we also know that it's absolutely got no chance whatsoever of being convergent, because mod of x times 1 is going to be greater than 1 in that case. Also for less than -1, again, we know it's got absolutely no chance of being convergent by the ratio test, because that limit is overall going to be greater than 1. Then we just need to check the two boundaries. So for the boundary x is equal to 1, of course, this series is then just going to be 1 plus 1 plus 1 plus 1, infinite number of 1s. So at x is equal to 1, it's not convergent. And then the case when x is equal to -1, that's a little bit more interesting. Not that much, but a little bit more interesting. So you've got 1 minus 1 plus 1 minus 1 plus 1. So this infinite series that I think fascinated people thousands of years ago, what is the answer to this? Is it 0 or is it 1? Well, the answer is it's neither. It doesn't actually have an answer. Because the rigorous meaning of what this series converges to is it's the limit of the sequence of partial sums. So if we think about what the sequence of partial sums is, so the partial sum 1 is equal to 1 because you've just added the first term, so that's 1. The second partial sum is 0 because it's 1 plus -1. The third partial sum is 1 plus -1 plus 1, which is 1 again. The fourth partial sum is then 0 because you've added on back -1, and it just goes on flitting between 1 and 0. And this infinite sequence that flits between 1 and 0, that doesn't overall have a limit. It has two convergent subsequences, one that converges to 1 and one that converges to 0. It has a limit superior and a limit inferior, but it doesn't overall have a limit. So it doesn't have an answer. That series is non-convergent as well. Non-convergent in a different way, though, to this one being non-convergent. This one truly diverges off to infinity, whereas this one is more, it is bounded. It's just flitting between two different answers, so overall doesn't have a limit. But it's still non-convergent. Both are non-convergent. And indeed, you can still use the word divergent applied to this. Divergent doesn't mean it's unbounded. It just means it doesn't have a limit. It means the same as non-convergent. In my opinion, we should use divergent differently. Divergent should mean it goes off to infinity, but it doesn't mean that is the rigorous meaning of it. It is synonymous with non-convergent. So this thing's radius of convergence is 1. It's convergent on that open interval centered around 0, so this open interval -1 to 1. So I'd just like to give one more example. So sum from I is equal to 0 to infinity of I factorial x to the I. So just writing out a few of these terms. So 0 factorial is 1. So we've got 1 plus x plus 2x squared plus 3 factorial, which is 6x cubed, plus 4 factorial, which is 24x to the 4, plus 5 factorial, which is 120x to the 5, etc. So this is actually going to be an example of a power series with a radius of convergence equal to 0. The only place where it's convergent is x is equal to 0, the place where it's centered around. Everywhere else, it's going to diverge. And let's just see how this is going to work. So if we think about then the limit as n approaches infinity of this ratio between the coefficients, so they're all positive, so we don't need to worry about absolute values. So it's going to be n plus 1 factorial over n factorial, which will cancel, and we'll have limit as n approaches infinity of just n plus 1, and of course that's unbounded. It's getting bigger and bigger and bigger as n goes to infinity. So its limit is infinity. So then if we think about the equation that needs to be satisfied, and goodness, I don't know whether that's a helicopter or a jumbo jet going over, I think it's a helicopter. The equation that needs to be satisfied then by x is going to be mod of x, and this is in quotation marks because of course this isn't real, this is a bit dodgy maths, multiplying by infinity, but the equation that we kind of need to be satisfied is mod of x times something that's infinity needs to be less than 1, and for most values of x that isn't at all possible, but for mod of x is equal to 0, this does actually work, and we need to clarify that because multiplying 0 by infinity is dodgy stuff. But if we go back up to our original problem, it was actually the limit of this thing times this thing. So if we pull mod of x back in as really it was in there beforehand, if mod of x is equal to 0, then the limit would never have been plus infinity in the first place because 0 would be multiplying all of these things. So actually, this limit is totally changed. It's actually just the limit of 0, 0, 0, 0, 0 in that case. So it never goes to infinity in the first place. So overall, the limit comes out as less than 1. So for x is 0, everything's saved. The limit is saved. It never goes to infinity. But for any other value of x, even if mod of x is tiny, it doesn't save this. This thing still goes off to infinity, even with that mod of x in there. So it's not salvageable. So for no other x is it going to be true that somehow that limit overall comes out as less than 1. So for all the others, this diverges off. So its radius of convergence is, if you like, 0. And in dodgy maths terms, you can think of it as mod of x needs to be less than 1 divided by infinity, and 1 divided by infinity in dodgy maths is kind of 0. So you then get that the radius of convergence is 0. Because our formula for the radius of convergence was this 1 over rho. So we've got 1 over infinity, so we get 0 as the radius of convergence. So the only place this is convergent is going to be x is equal to 0. Everywhere else, it's divergent. So we'll end there. Thank you for watching. Overall, what we have done is we have applied the ratio test for the convergence of an infinite series to power series, and from that we can actually often conclude for which values of x a power series is going to be convergent, and we find that often these ranges of the real line that satisfy convergence come in little intervals centered around the center of the power series, and we call this the radius of convergence. So thank you for watching.